Humans, even mathematicians, can handle a little bit of inexactness. Digital logic, not so much. If you've been watching any of the computer organization videos where we covered state machine design, you probably saw that I was insistent upon every single state having exactly one transition out of it for every possible input. When we're talking about discrete math, we didn't cover that quite as exactly as we did in computer organization. Let me show you exactly what I mean. And we'll start out with one of the good ones where there is a specific transition for exactly each of the inputs from every one of the states. Let's say that I've got a coin here, and then I do a series of coin tosses. And those coin tosses, in the sequence, I'm going to record the sequence, and in those coin tosses, I need to have at least one tails. Well, how would I represent that as a regular expression? So I have a tails, right? Well, before that tails happens, I can have any number of heads. After the tails, I should be able to have a sequence of, well, some heads, some tails, maybe nothing. So I can have heads or tails and any combination of them. So it could be an empty string. So in fact, I could flip a coin once, have no heads and none of the ones that follow, and just get that one tails, and we've got it. So what does our state machine look like that represents this particular regular expression? Well, remember, our state diagram must start off with an initial state, and that initial state is represented with an arrow. I'm going to call this initial state Q0. Now, as long as I keep getting heads, I am going to remain in that state. That state is just, we haven't gotten anything yet. Notice that there's no double circle representing an accepting state or a final state. Now, as soon as I get a tails, then I go to an accepting state. We'll call this one Q1. Now, once I get there, I'm good. And in fact, I can keep getting heads or tails as much as I want. Afterwards, I'm going to stay in that state. Now, this particular diagram I like because it says that I've got, for example, from state Q0, I know exactly where I'm going if I get a heads. I know exactly where I'm going if I get a tails. From Q1, I know exactly where I'm going if I get a heads. I know exactly where I'm going if I get a tails. Now, let's talk about the transition table. Remember, the transition table was this table which identified based on the current state and whatever our input was, whether in our input possibilities in this case are heads or tails. If we're in a current state, we know what state we're going to based on the transition, or based on the input, excuse me. So we start out with Q0 as our initial state. If I'm in Q0 and I get a heads, I'm going back to Q0. If I'm in Q0 and I get a tails, I know that I'm going to Q1. Notice that there's exactly one state I can go to. Now, I have only one other state to worry about for this transition table, and that's Q1. If I'm in Q1 and I get a heads, where am I going? Well, if I'm in Q1 and I get a heads, I'm going back to Q1. If I'm in Q1 and I get a tails, I'm also going to Q1. So notice every single one of these cells has exactly one state where I'm headed. In fact, we have another way of representing this called the transition function. And the transition function is usually represented with a little lowercase delta. And the lowercase delta has two arguments in that particular function. So one of them is the state, and the other one is whatever the input was. Now, for this particular state, and what's going to happen is I'm going to generate one or more states, or none or more states, that this could possibly go to. For this particular state transition table, notice that every single one of these transition functions, regardless of what my arguments are, we're going to one state. And so for this guy, Q0, heads, I'm going back to Q0. The delta function for Q0 tails, if I get a tails, I'm going to Q1. If I'm in state 1 and I get a heads, then I am going to state Q1. And if I'm in Q1 and I get a tails, I'm also going to Q1. Now notice the cardinality of the results for every single one of these is a size 1. That means that I've got, well, we'll talk about it a little bit later, but what we've got here is something called a deterministic finite automata. Let's change it a little bit and see if we can't get something that's a little less exact. We can make a slight modification to this regular expression to introduce a little bit of an inexactness to this regular expression or to the resulting state machine. Let's say, this one said I'm going to get at least 1 tails in a sequence of coin flips or coin tosses. What if I instead say that I want the first one to be a tails, all right? So it has to be, the first coin toss has to be a tails. Can be anything it wants to after that. Well, let's take a look at what the state diagram looks like. Once again, we're going to start out with an initial state. All right. Now, if I get a tails, then I'm going to go to my final state Q1. So that tails is going to bring me to the final state Q1. Once I get to Q1, then a heads or a tails is going to keep me in state Q1. What happens, though, if I'm in Q0 and I get a heads? There's no transition defined for it. And in order to develop our digital electronics that support this or realize this particular state diagram, we got to figure out exactly what's going to happen. So let's go ahead and draw out the transition table. So I've got my current state, right? I've got what happens if I get a heads, what happens if I get a tails, all right? Let's draw this table out. So if I am in Q0 and I get a heads, well, it turns out that the set of states we go to if we get a heads from Q0 is the empty set. Where do we go? Well, let's finish this out and we'll see if we can't answer that question. If I get a tails from Q0, I go to Q1. Now, my next state, Q1. If I'm in Q1 and I get a heads, I go to Q1. If I'm in Q1 and I get a tails, I go to Q1. Let's take a look at our transition function, delta. If I'm in Q0 and I get a heads, that goes to the empty set. If I'm in Q0 and I get a tails, that means I'm going to Q1. From Q1 with a heads, we go to Q1. And from Q1 with the tails, we also go to Q1. Now let's look at the cardinality of these resulting sets from this transition function. The cardinality for these bottom 3, 1, still okay. But we've got a cardinality of 0 for this top one. We don't have any idea where we're going. Turns out, however, there is an easy fix. And that easy fix is to create a state that represents we got nowhere to go. We couldn't figure out what the regular expression was. It is a failed regular expression. Now, remember, what we're going to do what we do to represent a final or accepting state in our state diagram is to put the 2 circles around it. But let's use an asterisk to represent the final state in our state transition table. What I'm going to do is create a new state. We'll call this Q2. And this Q2 is going to replace the empty set here. So instead of going to nothing, we're going to go to Q2, and Q2 is going to represent the failed situation. We didn't find or didn't realize the regular expression. And that really is that's not going to be a final or accepting state because we're not accepting the sequence of coin tosses. Now, this particular state, I'm going to just draw it here. We'll do Q2. We go to it if we get a heads from Q0. Now, once we've failed, once we have come up with a sequence that doesn't match our regular expression, there's nothing we can do to succeed, to find a regular expression that matches. So we are going to stay in Q2. So as long as once we get to Q2, if we get a heads, we're in Q2. If we get a tails, we're in Q2. And so this now changes our transition function. So our transition function now, if we get heads out of Q0, we're going to Q2. And now we'll also have Q2 heads is going to Q2, and don't really have room to put this. Well, let's see if we can. If we're in Q2 and we get tails, we're also going to Q2. Look at all 6 of those, each one, cardinality of 1, exactly one state where we're going to. Now we have the deterministic finite automata that the computer, or that can be realized in digital electronics. Let's make another slight modification to our regular expression. So this one said I get a tails followed by any sequence of coin tosses. Let's change this so that it is now any sequence of coin tosses, could be a ton of heads, could be a bunch of tails, doesn't matter, as long as it ends in a tail. All we're doing is we're just simply saying last coin flip, last coin toss has to end in a tails. Let's see what our regular expression translates to whenever we look at a state diagram. So we start out our initial state. So we've got Q0, all right? Now, this says I can get heads or tails. I can just keep getting them, any number of them, right? 0 or any combination of them, as long as the last one brings us to a tails brings us to our last state there. Turns out this is going to introduce another inexactness that doesn't have an easy fix like the other one did. Let's take a look at our state transition table. So we have our current state, right? And then what happens if we get a heads? What happens if we get a tails? There you go. Now, if our current state is Q0, well, if we get a heads, there's exactly one place we're going. We're going back to Q0, all right? But if we get a tails, there's actually a set that we can go to. We could be going to either Q0 or we could be going to Q1, all right? Now, when we look at our transition function, Q0, then that's supposed to be a 0. If we have a heads, we go to Q0. All right. If, however, we get a tails, we're going to either Q0 or Q1. Now, this cardinality of the first transition function is just one, right? There's one place. There's exactly one place we're going to. But this guy right here, we've got a set that has a cardinality of 2. There are 2 options. The computer doesn't like that inexactness. We're going to have to figure out a way to solve that problem. Now, we also have Q1. Now, if we're in Q1, what do? Well, turns out we can't go anywhere. If we've reached Q1 and have determined it to be an exacting, an accepting state, I guess you could say that a tails could bring you back here. But if you get a heads, then there's nowhere to go. It's the empty set. Let me go ahead and write down these last 2. So you have Q1 heads, that's going to bring us to the empty set, and then Q1 tails, that's going to bring us to, well, we could go to Q1, all right? There are a set of steps that we can take that can convert that non-deterministic finite automata to a deterministic one. And the steps go something like this. Step 1, remember that one of the components of a state machine is the set of all the states, all the available states. We're going to start out by creating a new set of states, and the initial contents of that new set of states is just our initial state. And in fact, what's important to understand, this state may, and in fact most likely will be, the only state that will be copied from our original non-deterministic finite automata. So first thing you do is you create a set of states that contains just Q0, just our initial state. Now, step 2, which is going to be part of a loop, step 2 says, grab one of the states that you have in this new set of states, and you're going to create its own row in the transition table, and you're going to figure out exactly where it goes based on all of our inputs. The important thing to understand, though, is that instead of creating sets of states, which really is going to happen, I mean, for example, when you have tails, you could go to Q0 or Q1. What's going to happen, though, is that set itself is going to represent a new state. In other words, all the possible destinations are going to be grouped together into a single state. I'll show you how that works with an example. Now, the third step. For each possible input from this new state that we have added, we are going to create all the states that we could potentially get to based on each one of our inputs. The combinations of sets, or even the empty set, those were going to be considered a state in themselves. Step 4. Any of the new states that we have created, we're going to add to our new Q prime, our new set of states. If we've added new states, we go back up to step 2 and just start the process. Pick a new state that hasn't been added to our transition table, add it to our transition table, figure out the new states that it goes to. I'll show you with an example. I'll show you with this example. If you get to step 2 and there are no new states that have been added to Q prime, you're done. Go down to step 5. Step 5 says that if one of these new states that we've created contains an accepting state as one of its sources, that too is going to be an accepting state. Well, let's go ahead and do the example using what we've got up here. So step 1, we are going to create our Q prime, and it is going to have our initial state Q0. All right. So, and I'm not going to put the closing brackets because I'm going to start adding more states to this, right? And then we're going to have our state transition table. So there's the current state, and then each one of our inputs, heads, tails. All right. Now, what is this going to look like? Well, step 2 said we have our initial state, which is the same initial state that we started out. And remember, there can only be one initial state. It's the same initial state that our old state diagram went with. Now, we will now do exactly like we did before. If I get a heads, I'm going to Q0. Well, that state is already included in Q prime. And then if I get a tails, I'm going to either Q0 or Q1. Now, that itself is actually going to be a new state. And so Q0, Q1, that is a new state. Since I've added a new state to Q prime, I go back up to step 2, which says create a row in the table with this new state. And so this new state, it looks like a set of states, but it's actually going to represent just one state. I'll show you how that works in a minute. Now, if I get a heads, I need to take the union of all the possible destinations from Q0 and all the possible destinations from Q1. So if I'm in Q0 and I get a heads, I'm going to Q0. If I'm in Q1 and I get a heads, well, remember, that went to the empty set. So the union of Q0 with the empty set is Q0. All right. Let me try that again. Basically, what you're looking for is you want to figure out all the destinations from heads from Q0, or union it with all the destinations from Q1 if you get a heads. Well, Q1, I didn't go anywhere when I got a heads, so the union is just the state Q0. Now, we go over to tails. The union of all the places that we can go from Q0 if we get a tails, well, Q0 can go to Q0 or it can go to Q1. And Q1, if I get a tails, goes to Q1. What's the union of that? What's the union of Q0 and Q1 unioned with Q1? Well, it's just Q0, Q1. All right. And so what I've got is, and it looks like it's going to be a simple modification. What I've done, I haven't added any more states here. And so I guess maybe I'm done, all right? And maybe what I've got is a final state machine, still has just two states, but we have some different transitions defined here. By the way, we sort of skipped over step 5, didn't we? Step 5 said we're going to determine all the accepting states out of this new state, out of this new set Q prime. We're going to figure out all the accepting states by looking at any of the states that were created, including the sets that were created that are combinations of states. And if the combination of states or that particular state contains a state that was an accepting state, it too is an accepting state. So Q0, not an accepting state. It was the initial state. It never was an accepting state, so it's going to stay not an accepting state. But since this new state, Q0, Q1, contains Q1, it too becomes an accepting state. So let's take a look at the state diagram. We've got Q0, which is still our initial state. And now we don't have Q1. What we have is a new accepting state, which is Q0, Q1. All right. This is this new one. Now, it probably would be a good thing for me to just go ahead and relabel them, but I just want to show you that this became a state in itself. Now let's do the transitions. If I'm in Q0 and I get a heads, I'm going back to Q0. If I'm in Q0 and I get a tails, I go to Q0, Q1. If I'm in Q0, Q1 and I get a heads, I'm going back to Q0. All right. If I'm in Q0 and I get a tails, I stay in, if I'm in Q0, Q1 and I get a tails, I stay in Q0, Q1. Does this make sense? Well, let's see. I'm looking for a sequence that ends in tails. All right. And so anytime the last item was a heads, it's going to bring me back to this Q0, which is not an accepting state, which indicates that string is not a member of the regular set that is generated by that regular expression. If, however, I get a tails, anytime the last thing I've done is a tails, I'm going to be in the accepting state. So a slight modification turned this from something that had an inexactness, an ambiguity, into something that for every single transition or every single possible input out of every state, we're going to a unique state, just one state. And this is our new state transition diagram that shows us how it works. Now let's look at our sequence of coin tosses and see if we can detect when it ends in two tails. What does our state machine look like? Well, it looks a lot like the one we had before, where we start out with Q0, that's our initial state, and as long as we get a heads or a tails, we stay in Q0. What brings us to our terminal state or our final state or our accepting state is actually two transitions, both requiring a tails. So as long as we can just keep receiving whatever we want to receive for heads or tails, but the last two is going to bring us to our accepting state of Q2 after two tails. So let's take a look at our state transition table. All right, heads, tails. What are we going to get? Well, I've got three states here. I've got Q0, Q1, Q2. All right. Now, if I'm in Q0 and I get, and the Q0, remember Q0 is our initial state. If I'm in Q0 and I get a heads, I'm going to Q0. If I get a tails, I'm going to either Q0 or Q1. So that's our set, right? Q0, Q1. If I'm in Q1 and I get a heads, not defined. So that's the empty set. If I'm in Q1 and I get a tails, I'm going to Q2. If I'm in Q2 and I get a heads, not defined. If I'm in Q2 and I get a tails, also not defined. Now, this is a perfectly legitimate representation of a state machine that will find that regular expression. It is, however, non-deterministic. We want to apply the steps that are going to give us the deterministic finite state machine from that non-deterministic one. So remember, we're going to start out by creating our set of states that contains only Q0, our initial state. So there's our current state. And what do we do if we get a heads or a tails? Well, in this case, we just go back to our table. We go to Q0 if we have a heads. If we get a tails, we come to this new state, Q0, Q1. All right, so yes, it is a set of states over here, but over there, it is actually representing a single state. Now, in the process, we have created a new state, and that new state, we're not going to go off of these guys anymore. We're going to figure out where to go to from this new state that we created called Q0, Q1. Now, to figure out where we go to from this new state Q0, Q1, if we have a heads, we have to figure out where we go if we're in Q0 for a heads, and where we go if we're in Q1 for a heads. Well, if we're in Q0, we go to Q0. If we're in Q1, we go to the empty set. So the union of these two is just Q0. And we didn't create a new state. We've got Q0. So what's going to happen is if we land in Q0, Q1 and we get a heads, we're going to go back to Q0, our initial state. If we are in Q0 and we get a tails, Q0, we get a tails, we go to Q0 or Q1. If we're in Q1 and we get a tails, then we're going to Q2. So the union of those two sets, or the union of those two results, is going to be Q0, Q1, Q2. And we've created a new state. So we take this new state, we add it as the next row of our transition table. All right. And now we're going to do the same process, figure out the union of where we're going to if it's heads from any one of those three states in order to figure out the destination for heads, and we're going to do the same thing for tails. So if we're in Q0 and we get a heads, we're going to Q0. If we're in Q1 and we get a heads, we're going to the empty set, nothing. If we're in Q2 and we get a heads, we're going to the empty set, nothing. So the union of those three results is just Q0 still. If we're in Q0 and we get a tails, we're going to Q0 or Q1. If we're in Q1 and we get a tails, then we're going to Q2. If we're in Q2 and we get a tails, we're going to the empty set. So what's the union of all three of those? Well, it's Q0, Q1, Q2, Q0, Q1, Q2, and we haven't created a new set. We haven't created a new state. That state already exists. We've just defined that row in the transition table. Now, the one thing that I forgot to add over here was identifying Q2 as a final state. And so you go through all of our lists of states here, and if any one of them contains Q2, it too is a final state. The last row here is the only one for which that fits. Now, if I were making something a lot neater here, I would actually reassign these states different names. So maybe I'd say, this would be Q4 and this would be Q5 and draw something nice and neat. But I think to keep this straightforward, I'm just going to go ahead and keep my three states, Q0, Q0, Q1, representing that row, and then the final state, Q0, Q1, Q2, representing that third row. Now Q0 is an initial state. Q0, Q1, Q2, that is a final or accepting state. Now I just need to fill in the transitions. But this transition table has shown me I have exactly one destination for each one of the inputs. So if I'm in Q0 and I get a heads, I'm staying in Q0. If I'm in Q0 and I get a tails, I'm going to Q0, Q1. So I have exactly two transitions. What you're looking at is the cardinality of the input alphabet. So I have a cardinality of 2, heads or tails. That's exactly the number of transitions out of Q2 that I'm looking for. Now, if I'm in Q0, Q1, if I get a heads, I'm coming back to Q0. If I'm in Q0, Q1, and I get a tails, I'm going to that last term of that final accepting state, Q0, Q1, Q2. All right, so I've got 1, 2. I've got my heads, I got my tails coming out of Q0, Q1. Now I need to figure out my heads and tails coming out of Q0, Q1, Q2. If I'm in Q0, Q1, Q2, and I get a heads, I'm headed all the way back to Q0. If I'm in Q0, Q1, Q2, and I get a tails, I stay in that accepting state. And this guy kind of makes sense, right? I mean, what you're looking at is if I get 2 tails in a row, I'm going to end up in my accepting state. And as long as I keep getting tails, I'll stay in my accepting state. As soon as I get a heads, I am going to reset and start looking for those 2 tails in a row again. Resetting basically means I'm coming back to Q0. Now, in a later video, I may come up with a more complicated non-deterministic finite state automata to convert to deterministic. But for now, you have the steps that it takes in order to convert one of these ambiguous non-deterministic finite state machines into a deterministic one. Your digital electronics will thank you for it.